So today we are going to start with entropy. Okay, so yeah, generally we drawn one cycle. Okay, 1a to b1, okay, and 1a to c1. Okay, these are the two cycles. Okay, and if you want to draw the reversible cycles, then we are going to represent with the dark line, and we are going to draw the irreversible cycle then with the help of the dotted lines. Okay, all right. So when all the processes are reversible, then we can say that particular cycle is reversible. In a cycle, if there is one process which is irreversible, then we can say that total cycle is irreversible. Okay, so this is the thing. Okay, so next we are going to discuss about the first concept, that is for the reversible cycle. We are going to, as we did in the first law, second law. Okay, what we did, we took the first law for the cycle, and using the mathematical technique we derived the property. That property was internalization. Same we are going to do here. Okay, so generally if I want to take, if I take this cycle, so if I apply the Clausius inequality, what is Clausius inequality? Cyclic integral of dq by t equal to 0, which is for reversible process. Now if I apply this, then dq by t 1a2 plus dq by t 1a2 1b2 2b1 dq by t 1a2 dq by t 2b1 equal to 0. Okay, again for next cycle, that is 1a2 dq by t 1a2 plus dq by t 2c1. okay, this is the thing. Okay, now if we subtract this, we'll get dq by t 2b1 minus dq by t 2c1. dq by t 2b1 equal to dq by t 2c1. So this, as you can notice here, key between two endpoints 2 and 1, between 2 endpoints 2 and 1, this the value of dq by t is not changing for any process. Okay, as you can see, 2b1 is different process, 2c1 is different process, right? So dq by t values is not changing. So this value is the entropy, ds. Okay, this value, this is value, this is the quantity which is equal to entropy. Okay, this is not entropy, actually the value which is equal to entropy. So as you can notice here, this is valid for a process or a cycle. So as you can see here that there is no a point in the present here. If a point is present, then it completes a cycle, right? So this is for a process. Okay, that what I wrote here. Okay, it must be a property which does not depend upon the path followed by the system. So it means that if I draw the number of paths in the cycle, there are number of processes. So for each and every process, the entropy value will be same. The quantity which is equal to the entropy is same. So ds equal to dq by t reversible. Okay, this is the concept. Right. So for the irreversible process, what we are doing, so we are taking the same cycle, but here 2c-1 is irreversible process. Okay, now if I apply the Clausius inequality, suppose for example if you look for the cycle 1a to b1, so this is a reversible cycle, right? So dq by t 1a2 plus dq by t 2b1 equal to 0. Then dq by t 1b2 dq by t 1 2c1. So as you can look in this second cycle that there are dotted lines. Okay, so it means that this cycle is a reversible cycle. Okay, it means that this cycle is a reversible cycle. Okay, so because there is one process which is irreversible, it means that whole cycle will be reversible. Now if I apply it here, I will get 1a2 c1 1 dq by t 1a2 plus dq by t 2c1 must be less than 0. Okay, so if I do the substitution, I will get 2 dq by t 2b1 is greater than dq by t 2c1. As we know, dq by t 2b1 was the value which was equal to the change in entropy. Okay, ds is greater than dq by t. So from here what we are concluding, actually we are concluding that dq by t reversible is not an entropy. Its value is less than entropy. Okay, it has a value which is less than entropy. Alright, so this was the concept. So what we did here, we tried to remove remove the we try to remove A, so it will become valid for the process. Okay, that's what we did. Okay, so for reversible cycle and irreversible cycle, we took the two cycles, and we took the two cycles. For reversible process, we took two reversible cycles. For irreversible process, we took one reversible cycle and one reversible process. And finally, we concluded for reversible process that dq by t reversible is entropy. The value of dq by t reversible is equal to the entropy ds. Okay, so from here we concluded that dq by t irreversible is not the entropy, but it is the value which is less than the entropy. Okay, this is the thing. Next we are going to discuss what is entropy. What is entropy actually? In the examiner we will tell what is entropy. Okay, so how will you answer this? Before answering this thing, let us discuss one most important point, that suppose for example if there are number of processes are present, there are number of cycles are present. Okay, one cycle I took reversible cycle, and next all I took irreversible cycles. Okay, there are some reversible process and there are some irreversible process. Two are reversible, two are irreversible. So for example, if I tell you that dq by t 1a2 the value is 5. Now can you say me dq by t 2b1? What is dq by t 2b1? Value of dq by t 2b1, you will say that it is 5 because the process is reversible. If I tell you dq by t what is the value of dq by t 2c1, it is irreversible, so it can't be 5, right? It will be less than 5. Okay, it will be less than 5. Okay, say 4.5. Okay, what about dq by t 2d1? Its value will be less than 5. It will be greater than 4 or less than 4, but it will be less than 5. Okay, it will be less than 5. So what I am going to conclude here is that dq by t value for the reversible process will be same. For the irreversible process it may change. Okay, for the irreversible process it may change. If there are two irreversible process, one irreversible process dq by t value is 4.5, you can't say that second irreversible process also has a 4.5. It will be less than 5. It may be greater than 5, it may be less than 5. Now next question I will ask you, that what is the change in entropy for the process 1a2? It is 5. What is the change in entropy for the process 2c1? It will be 5. What is the change in entropy for the process 2d1? It will be 5, because change in entropy your focus will be goes on dq by t irreversible. Dq by t irreversible we got 4.5. It will be less than. No, it is not like that. Okay, dq by t irreversible is not the entropy. It is the value which is less than the entropy. Okay, entropy is same for each and every process. For reversible process, for irreversible process, each and every process the entropy value will be same. Sorry, the entropy will be same. Change in entropy will be same, because change in entropy gives a property. Okay, dq by t irreversible is not an entropy. It is a value of the entropy which is less than entropy. It is a value which is less than entropy. Okay, so if process in between 2 points, if there are number of reversible process and irreversible process, then the change in entropy will be same. Okay, so I think you understood. Okay, suppose for example if there are in a cycle there are two endpoints. In the two endpoints there are two reversible process. Okay, dq by t value for the reversible process will be same, but dq by t value for the irreversible process will not be same as the reversible process. It will be less than the irreversible process. Also it will not same for the all the reversible processes dq by t value. Okay, so what about entropy? Change in entropy value for each and every process, whether it may be reversible or irreversible, the change in entropy will be same. Why? Because entropy is a property. It does not depend upon the path followed. It only depends upon the endpoints. Okay, that is the thing. So now in the interview he will ask that what is entropy. Okay, so you should tell between two endpoints, if there are number of reversible process are there, then for each reversible process the quantity dq by t is same, which is known as entropy. Okay, between the two endpoints the number of reversible processes are there. For each reversible process the value of dq by t is same, which is entropy. It is known and is called entropy and is known as entropy. Okay, so what about dq by t reversible? Dq by t irreversible dq by t irreversible, it is a quantity which is less than entropy. Okay, so what is entropy value for the entropy value for the irreversible? It is same as reversible process, because it depends upon the part. How to calculate the entropy change for the irreversible process, entropy change for the irreversible process? So then we have to replace it with a reversible process. Okay, so this was the concept, basics. So after talking about the entropy, let's talk about the entropy change for the reversible process. Okay, so what is the entropy change value for the reversible process? That is dq by t reversible, right? So yeah, so entropy change will be equal to dq by t reversible. So if you, there are three cases. If we add the system, if we reject the heat, and if heat is constant, if we add the heat, then dq value will be positive and t is positive because it is greater than absolute zero. Okay, we are taking reference as absolute zero, it is greater than absolute zero temperature. So temperature will be positive, and also ds will be positive. If ds and t is positive, then entropy change will be positive. If entropy change will be positive, then s2 will be equal to greater than s1. Okay, s2 will be greater than s, entropy will increase. So if you reject the heat, dq will be negative and dt will be dq by t, right? T is positive, so entropy will decrease. If entropy decreases, then s2 is less than s1. In the third case, the dq by t, q is 0, right? Q is it means that ds is 0. If ds is 0, then s2 equal to s1. It means that entropy is constant. It means that for each and every reversible process is an isentropic process. Okay, this was the conclusion from the reversible adiabatic. Okay, so entropy of the system, from here we can observe the entropy of the system may increase, may decrease, or may become constant. Okay, so next we are going to discuss about the entropy change for the reversible process. So what will the entropy change for the reversible process? Suppose for example, if I tell you that if x is less than y, okay, so what I should do to make x equal to y? So I should add somewhat to y, right? Some fraction to y, so that it will be equal to x, right? So similarly, if dq by t ds is greater than dq by t reversible, then I should add some fraction to the dq by t irreversible, right? So to make the value which is equal to the entropy, so that value is delta S generation. Okay, we are adding to make, we are adding. Okay, if we add it, we will get the particular entropy value. Okay, so delta S generation, it is known as entropy generation. Okay, entropy generation. So it will be positive or it will be 0, but it will not be negative. Okay, so again, if I want to look at in from another angle, so if delta H generation is 0, then I can say that dq by t dq by t equal to ds na? So when delta H generation will be 0, if the process is reversible, and if delta H generation is positive, then the process will be irreversible. Okay, that is the thing. So again, the next discussion was कि dq by t, actually delta generation के बारे में बात करें तो actually we drawn one cycle, right? So for process 2c-1, what was the entropy value of the dq by t irreversible? It was 4. Okay, what was the actual value for the actual entropy change in entropy value? It was 5. So the difference is 1. So irreversibility is delta generation is 1. Okay, now 1. So for the process d dash, for the process d dash, dq by t value was 4.5, and that value entropy change in entropy value is 5. So 5 minus 4.5 is 0.5. From here we can observe that delta generation value is changing, right? So between the two points it is changing. Okay, for each and every process it is changing. It means that it is following the path. Okay, so it is not a property, it depends upon the irreversibility of the system. Suppose for example, if process is more reversible, then I can, if the process is more irreversible, then I say that its delta H generation is more. If the process is less irreversible, then I can say delta H generation value is less, and the process is reversible, then it is 0. Okay, that is the thing. Okay, that is all about the delta H generation. And mind you that delta H generation is always positive. Why delta H generation is always positive? To answer this question, we must actually, this is the one point, right? So this is the one point, but that and the next point was that how we derived it. We derived it like ds. First of all, we got ds is greater than dq by t irreversible. So we are adding some we are adding some fraction to dq by t irreversible to make it to make the whole quantity which is more quantity, to make it the whole quantity equal to the dq by t reversible, right? So we are adding the term, that term is delta H generation, we are adding it, okay, we are not subtracting it, okay. So that is the thing. So delta H generation, either it must be 0 or it must be positive. And in the sense, in the common sense, you can see that delta H generation is positive, right? So it depends upon the irreversibility. Irreversibility comes due to friction. Okay, if the friction is very more, then reversibility will be more. If the friction is very less, then reversible. When we can say the process is reversible when it is slow process, when it is slow and okay, yes. All right. So entropy change for the reversal process we discussed, I think. Okay. Yeah. When heat is added to the system, when the heat is added to a reversible process, you just don't need to multiply this formulas. Okay. Or you do one thing, just remember the result. Okay. We are applying cyclic integral of dq by t. ds is greater than ds is greater than dq by t irreversible, right? So for balancing, what we did, we added delta S generation. Okay, so if we add heat, q will be positive, t is positive, and delta S generation is always positive. Okay, it may be 0, it will be positive. If it is 0, then process is irreversible. But we are not talking about the reversible process, we are talking about the irreversible process. So delta H generation is 0, positive. So dq is positive, t is positive, so entropy will increase if we add heat. If we add heat in the reversible process as well as in the irreversible process. What about if we reject the heat? If we reject the heat, look, that dq is negative, t is positive. Okay, so first term is negative 9. Then it comes to delta H generation. Delta H generation is not a property. It follows the path. Okay, it is not constant actually. Okay, it will depend upon the irreversibility, right? It will be greater or it will be less. Suppose for example, if the sum is coming as positive, then we can say that entropy is increasing. If the sum is coming as negative, entropy is decreasing. If the summing is coming as 0, then we can say that the entropy is constant. Okay, so from here we come to know the entropy will increase or decrease or become constant in if we reject heat in the irreversible process. So it means that previously we discussed about the reversible adiabatic process, there entropy was constant, here also entropy was constant. So reversible adiabatic process is an isentropic process, but every isentropic process is not a reversible adiabatic process. It may be irreversible heat rejection process. Okay, because here we are seeing that case that entropy is constant if we are rejecting the heat in the irreversible process, by making sure that delta H generation is same as dq by t irreversible. Okay, this is the thing. So now next we discuss about the third case, that is irreversible adiabatic process. So dq is 0, then entropy generation is positive, so entropy will increase. Okay, so we discuss about the cases where entropy increases. Entropy increases if you add heat, if we add heat in the reversible or irreversible. If we reject heat in the irreversible process, that may be the case. Okay, if the process if there is irreversible adiabatic process, then also entropy will increase. Okay, so that is the case. Okay, so now from here we are going to decrease when the entropy will increase or decrease. Okay, that is the thing we are going to discuss here. Okay, so next, entropy change for the isolated system. Entropy change for the isolated system. So entropy change in the isolated system in the sense where dq is 0 and dw is 0. Okay, if we apply ds is greater than or equal to, ds will be greater than or equal to dq by t, right? So dq is 0, so ds of an isolated system will increase or it will be equal. Okay, best example for the isolated system is universe. Okay, entropy of the universe always increases. Okay, this is the case. Now this gives the direction of the feasibility. Okay, principle of increase of entropy, it says that for the system entropy may increase or decrease or become constant. For the surroundings entropy may increase or decrease or become surroundings. But for the whole, for the whole universe, for the whole ds of universe, entropy will always increase. Okay, entropy never decreases. Entropy may become 0 or entropy may be positive, but entropy never decreases. Okay, criteria for the feasibility of the process, it gives the criteria for the feasibility of the process. Now from here we are discussing about the processes. Okay, So in the second law we discussed about the cyclic integral of dq by t, whether the cycle exists or not, whether cycle is possible or not possible, whether cycle is reversible, irreversible, or possible or not possible, discussed in the second law. But here we are only discussing about the process, okay, whether the process possible not possible, we can say by calculating ds of universe. All right, if ds of universe is coming as positive, then it is process is irreversible. If it is coming as 0, then the process is reversible. If it is coming as negative, then that process is not possible. Okay, this is the concept of principle of increase of entropy, which gives the further the concept of whether the process is possible or not. Okay, suppose for example, if the room is our system, okay, if the room is our system, if we add 10 kilojoule of heat, then surrounding must reject 10 kilojoule of heat according to first law of thermodynamics. It must reject the 10 kilojoule of heat, then only we are adding 10 kilojoule of heat. Okay, if we add 10 kilojoule of heat, then what happens to the surroundings system? Entropy of the system will increase if we add it. Okay, whether it may be reversible or irreversible. But what about surroundings? Entropy of the surroundings will decrease. Okay, entropy of surroundings will decrease. So suppose for example, if we are adding 10, how to find out the generally how to say that system is possible or not, or reversible or irreversible. Process is system, not system, but process. Okay, suppose for example, 10 units of entropy is decreased, 10 units of entropy is added, then if we if is entropy of system minus surroundings, right? So entropy of system plus surroundings, plus surroundings. So it is rejecting 10 units. So 10 minus 10 is 0, process is reversible. 10 minus something positive, process is irreversible. 10 minus 10, 10 minus 12 minus 2, okay, process does not possible. Okay, so every process in the it takes place in the direction of increase of the entropy. Okay, this is the concept of isolated system. Okay, we'll discuss again. Okay, all right. So discuss मत कर भाई किसी से भी चीज़ है, ठीक है? That is a wastage of your time actually. Time is very very precious and it is important. So don't need to go into the telegram and discuss with other people the concept which you know. Okay, that is your advantage. It will be your advantage. Don't give your advantage to the others. Okay, don't discuss the concepts that you know in the telegram. You can ask actually हो रहा क्या कि I am going in the telegram and I am asking them, okay, कि ये क्या है actually you know actually. So कई को पूछ रहे हैं ताकि उन लोगों को अगर से नहीं मालूम रहा तो ताकि you will get an idea that they don't know this concept. एक वो हो सकता, ठीक है, और दूसरा वो है बट बोलना नहीं चाह रहा, ठीक है, for your favor, for your satisfaction you are telling. Okay, right, actually that is boosting your confidence, but that is not good actually, because you are wasting your time unnecessarily. Okay, so don't discuss that concept that you know. Okay, just uh, just to study the concepts and don't share with anyone. Okay, if they ask you any doubt, then you can you can check. Okay, so next we are going to look at one example. Okay, we discussed about the entropy for an isolated system. Okay, entropy for an isolated system we discussed. Next we are going to move towards one example. Okay, suppose for example I will take an isolated system. For an isolated system, suppose A is one chamber and B is another chamber. Okay, A is one chamber and B is another chamber. Okay, TA and TB. So what you are going to do now is that key suppose the heat is transferring from A to B. Okay, A to B. Suppose the temperature of chamber A is TA and chamber B is TB. Okay, this is an isolated system. Okay, so according to second law, so what must be the correct statement? TA is greater than TB, TA is less than TB, T equal to TB. So as we notice here, the heat is transferring from chamber A to chamber B. So from the Clausius statement, uh, without any external device, you cannot run the engine which is extracting heat from the lower temperature sink and giving it to source. Okay, without any external device. So it gives the direction, right? So temperature always flows from the heat always flows from a higher potential to lower potential. So TA must be greater than TB. Okay, that is the second law, right? So in order to prove that second law from classes you know, but in order to prove with the entropy gives the feasibility, possibility of the system also. Also according to entropy, ds of universe equal to ds of chamber A plus ds of chamber B. Okay, ds of chamber A. So entropy of the chamber is decreasing actually because heat is transferring from chamber A to chamber B, right? So minus dq by Ta plus q by Tb. You will get q Ta minus Tb by Ta into Tb. So if Ta is equal to Tb, then what happens? ds of universe becomes 0. Okay, there is no entropy change. Okay, no entropy change, and also heat will not flow. And if Ta is greater than Tb, Ta is greater than Tb, then heat will flow. Then entropy will be positive. ds will be positive. If Tb is greater than Ta, then this process is not possible because it violates the second law. Also, it violates the principle of change, principle of increase of entropy. Okay, principle of entropy. So this was the concept. Now one question is that generally when you are when you are throwing water on the floor, when you are throwing water on the floor, the water evaporates. Okay. Up next discussion is about reversible and irreversible. Okay, reversibility and irreversibility. Okay, so before discussing that thing, we will go into depth. Okay, first of all, if you take about the isothermal process, in the isothermal process, how the heat transfer takes place. Temperature is constant, right? How heat transfer will take place? Heat transfer is due to heat transfer is due to temperature difference. It is the transit form of energy which flows due to temperature difference, right? So in isothermal process, temperature is constant. Then how heat will flow? Heat will flow from surrounding to the system. Okay, from surrounding to the system. But in the system, if heat is added to the system, then to keep the heat temperature constant, the piston will expand slowly, and energy is added very less. Okay, so the temperature will be constant, and the piston will expand. Okay, in order to keep the temperature. Similarly, in the latent heat, what is latent heat actually? Suppose you took one you took one ball and you heat the water in the ball, and you heat the ball till water gets 100 degrees centigrade. Now the temperature of the burner is 500 degrees centigrade, suppose for example say it. Okay, so temperature of the water will be 100 degrees Celsius itself. Okay, it will boil now isothermally. The water is going to evaporate, so that is the phase change, right? So in the phase change, what happens? That is the isothermal process. So system's temperature will be constant, but that heat transfer takes place due to temperature difference between the surroundings and system. Okay, and if the heat transfer, so what is heat transfer actually? Heat transfer, it is a reversible process, reversible process or irreversible process. So it depends upon the temperature, right? So heat transfer due to finite temperature difference is a reversible process. Heat temperature due to infinitely small temperature differences is known as reversible process. Okay, don't ask them any doubt. Don't ask any doubt to them. Don't share your concepts. एडवांटेज उनका हो रहा एक्चुअली. यू लुक कि अगर से तो कॉन्सेप्ट शेयर कर रहा कि दे आर नॉट हैप्पी एक्चुअली. दे आर इन देयर ईगो है इन लोगों के पास कि दे आर स्टूडेंट्स ऑफ मेटेज, राइट? सो यू आर नॉट द स्टूडेंट ऑफ मेटेज, राइट? सो एक्चुअली उनके पास ईगो है. दे आर थिंकिंग दैट अरे ही नोज बेटर देन अस, देन वी आर द स्टूडेंट्स ऑफ मेटेज, देन हाउ ही नोज. ऐसा इन लोग जलावा होला. ओके, सो डोंट शेयर द कॉन्सेप्ट. शेयर करने से उनका एडवांटेज है ना, बट दैट इज तेरा एडवांटेज नहीं है. तो उनका एडवांटेज है बट दे आर शोइंग देयर ईगो, मीन्स that is their fault. It is not your fault, but don't share the concept, don't share anything with anyone. Okay, all right, commitment कर ले बस. Next, heat transfer process is for reversible or irreversible. It depends upon the temperature. If there is a finite temperature difference, then it is irreversible. If it is infinitely small temperature difference, then the process is reversible. Okay, reversible. So generally what is happening here कि So why heat transfer is process is reversible process due to finite temperature difference means uh, why the process is reversible? Because entropy gives you the proof. What is the proof for this? The entropy. Okay, we derived the thing, right? Ta is greater than Tb. So if the Ta is greater than Tb, positive, so entropy will increase. Ds is positive, Ds is positive, the process is reversible process. Ds is 0, then process is infinitely small temperature difference. Ta is nearly equal to Tb, and Ds will be equal to 0. So in the sense, entropy will be 0. So that means that heat transfer is reversible process. Okay. So actually PMM3 concept of PMM3 is that these are UIs which achieve perfectly reversible process. In the olden days, people used to believe that we can achieve a reversible process, but we can't achieve the reversible processes. Ta equal to Tb, delta is equal to 0. Alright, but we can't achieve. Suppose for example, in the examination it will ask you that which process is more irreversible. You have to look at delta T. If delta T is way more, then the process will be more reversible. Delta T is very less, the process will be more reversible. Okay. And if you give the one student key 20 degrees centigrade water, and if I tell that key increase the temperature to 80 degrees centigrade, we will attach to the reservoir and we will increase the temperature within single step. Okay. The next student, what he does, he takes the water and he increases 1 degree. Which process is more reversible? It's the second process. Which process is more irreversible? The first process. Okay. This is the concept. Next, reversible process are quasi-static process. These are the frictionless process. These are very slow process. Okay. Irreversible process are due to friction. Okay. Due to when the combustion is taking place, the main reason for the reversibility is friction. Okay. When there is a degradation of energy, the quality of the energy decreasing, then process is said to be irreversible. Okay. From high grade energy we are converting high grade energy, process is reversible. From high grade energy we are converting low grade energy, process is reversible. What is high grade energy, low grade energy? High grade energy as energy we can convert totally into heat, totally into different form of energy. Like suppose for example work we can completely convert into heat, but heat we cannot completely convert into work. Okay, so work is high grade energy, heat is low grade energy. High grade energy we can completely low grade energy, but low grade energy we cannot complete into high grade energy. Electrical work is a high grade energy. Suppose for example if I take the motor and if I supply the power to one, there will be small losses, right? I square RT losses. That is high grade energy. That is reversible process. Suppose spring is a reversible process. Spring stores the energy. Okay, it is a reversible process. So and also spring stores the energy inside. So it will be the process will be reversible. Next, reversible process. Suppose the generator shaft is connected to some motor shaft. So there will be sudden losses, but efficiency is very more. So process is more reversible. Okay, that is the thing. So work, kinetic energy, potential energy, etc. all are reversible process. But now I will give one example that if I drop the water on the floor, what is the temperature of the water? Room temperature. What is the temperature of the air? Room temperature, right? 20 to 28 degrees centigrade. Now water will evaporate. Why water will evaporate? Because water will evaporate in certain hours. Okay. So why? Because there is a heat transfer will take place. Okay. There is a phase change. So that is more reversible process. Okay. That is reversible process. Okay, this is the concept of reversible. इसमें खाली reversible irreversible discuss करें. Okay, in the revision we will discuss the whole thing. ठीक है, अगर से मैं ऑडियो बनाए तो और एक ऑडियो बना सकता हूँ दोनों को कंबाइन करके एंट्रोपी और सेकंड लॉ को. ठीक है, एंड इफ आई अगर से हो सका तो और एक ऑडियो बनाता हूँ 20 मिनट्स की, 15 मिनट्स की, 10 मिनट्स की. ओके, अवेलेबिलिटी भी ख़त्म हुआ तो 3 टॉपिक्स को पकड़ के एक ऑडियो बना. ठीक है. Okay, so we'll discuss the next thing, next concept. Okay, next temperature entropy diagram. Okay, at any particular temperature T, if you transfer dq amount of heat, okay, then generally what is the meaning of dq by T? What is T actually there? at any particular temperature T, if we transfer dq amount of T, then small change in entropy is ds, which is given by ds equal to dq by T reversible. Okay, this is the meaning of the T. Okay, so generally for small entropy at any particular temperature, the change in entropy, small change in entropy is found out by equation. But if we need total change in entropy, then what I must do? I must integrate. Okay, I must integrate this function. Okay, if I manipulate this, it will become TDS equal dq equal to TDS, right? dq equal to TDS. So actually there is a temperature axis and ds axis, temperature axis and entropy axis. Okay, there is a function. Generally if I integrate this function, then I will get value of total, then I will get value of total dq. Okay, total heat supplied for the particular process I will get. Okay, dq will be equal to integration of TDS from 1 to 2. Okay, this is the equation which we are getting. Okay, so from here we come to another, we studied about the that PV diagram. Okay, PV diagram, that area projected on the volume axis gives you net area projected on the volume axis for a particular process gives you the work done for that process. Similarly, area projected on the volume axis gives you closed system reversible work. But here area projected on the entropy axis in the TDS diagrams gives you heat transfer for that particular process. So, and the fourth thing which we discussed, that for the total cycle, total area of the cycle in the PV diagram gives you net work transfer, and the total area in the TDS diagram gives you net heat transfer. According to first law, net heat transfer will be equal to net work transfer. Okay, so dq will summation of q will be equal to w, right? So this area will be same, values will be same. Okay, this was the important concept. Next we are going to study about the representation of the Carnot cycle on the TS diagram. Okay, representation of the Carnot cycle on the TS diagram. So 1 to 2 process is adiabatic process. So PV diagram we come to know that, and for adiabatic process 1 to 2 adiabatic expansion compression process. Okay, we are compressing. Now isothermal expansion process. So in isothermal expansion is only possible when you add heat, so it will expand. Again adiabatic reversible adiabatic expansion process, then isothermal compression process. In the compression process is possible when we reject the heat. Okay, so this is Carnot diagram. So generally if you want to draw the TS diagram, then first of all, first process is reversible adiabatic compression process. In the adiabatic compression process, reversible adiabatic process is isentropic process. Then entropy will increase or temperature will increase or decrease in the compression. Of course it will increase, right? So 1 to 2. Next to process 2 to 3 is isothermal expansion process. In the expansion process we are going to add the heat, right? We are going to add the heat addition process, entropy will increase. Okay, so 2 to 3. Next, reversible adiabatic expansion process. In the expansion process, reversible adiabatic isentropic. Now temperature will increase or decrease in the expansion, it will, of course it will decrease. So 3 to 4. Again 4 to 1 isothermal compression process. So in the compression process heat is rejected. If the heat is rejected, then entropy will decrease. Okay, so this is the diagram. So if I want to find out the heat added, then what I must do? I must just take the TDS equation and just find out the area below the curve from the process 2 to 3. Similarly, if I want to know how much heat is rejected, then I must take the projected area on the TS for the process 4 to 1. Okay, so this is all about the representation of TS diagram. Okay, so from here W net will be equal to Q1 minus Kr. Qn will be equal to T into DH. Sorry, TH into DH minus TL into DL. DS. So DS which we take on TH minus TL. Okay, so efficiency will be equal to W output by input. Output we are getting W. So W by QH. Okay, W by QH. So this we can write as 1 minus QL by QH. QL can be written as TLDH by THDS. DS cancel, 1 minus TL by TH. Okay, This we are getting. Now the most important discussion starts. Okay, so combined first and second law. Okay, combined first and second law. So uh, why we are going to analyze this thing? Okay, so first thing is that we are going to derive such a equation which is possible for both reversible process and irreversible process. So generally when we look at the first equation, dq equal to du plus dw, this is valid for both reversible process and irreversible process. This is the equation of first law of thermodynamics, right? Next equation is dq equal to du plus pdv, dw is pdv, dw is pdv. This is valid for closed system reversible process, right? This was valid for closed system reversible process, dw equal to pdv. And the equation dq equal to du plus pdv, this valid for only for reversible process. We will discuss why it is valid for only reversible process. Next, dq equal to tds equal to dq. Okay, if you substitute, you will get tds will be equal to du plus pdv. Now if you notice the specialty of this equation, tds all are point functions. Okay, again this is valid for both reversible process and irreversible process. Now the discussion starts. Why it is valid for reversible process and irreversible process? Since tds is equal to dq, this is valid only for reversible process, and also dq equal to du plus pdv, this is valid for only reversible process. Then how you are going to say that this is valid for reversible process as well as irreversible process? So why it is valid for the both? So first of all, let me take one room. Okay, one room, there is one reversible process. In that reversible process, suppose dq amount of heat is, if I added 10 kilojoule of heat, so change in internal energy is 5 kilojoule, and dw value is w value is work done is 5 kilojoule. Okay, according to first law, 10 equal to 5 plus 5, that is 10 equal to 10. This is value. Okay, first law satisfied. Now what I am doing, I am changing the process. So if I change the process, dq, does the value of dq changes? I am going to replace the reversible with the irreversible process. Does the value of dq will change? Of course it is going to change. Suppose 8 will be the change in the value. Again du will change? Du will not change. Why du will not change? Because du is the property. It depends upon the endpoints, right? As the entropy is a property, entropy value will not change for reversible process as well as irreversible process, right? If in between the cycles, if there are number of processes, reversible, irreversible, and each and every process, then the value of entropy will not change. Why? Because entropy is a property. It depends upon the endpoints. Okay. So similarly here, du value will not change. Next, coming to us the w. W will change or not? dw is going to change or not? Of course it is going to change, because dw is a path function. dw is a path function. Okay, it depends upon the how the path is followed. Okay, how it is achieved, right? So suppose for example it is 3, say. So now if you apply the equation first law, 8 equal to 5 plus 3, that is 8. Okay, first law valid. Now what I am going to do is, this our first equation and second equation, first equation is satisfied, right? If we change the process, next we have satisfy the second equation. Now dq will be, dq was 5, dq was 8. If you change the process, it was 8, right? So what is du? Du was same, it will not change, 5. Again pdv, if you look at pdv, it was equal to 5, right? It was equal to 5. pdv was equal to 5, so it will not change because it is a property. Now 8 equal to 5 plus 5, so this equation is not valid for irreversible process. Satisfied? Are you getting my point? dq equal to du plus pdv, this is valid only for the reversible process. What I did, I changed the reversible process to the irreversible process, so dq value is reduced. Okay, so from the analysis I come to know that dq was 5, dq was 8, du was 5, and pdv was equal to reversible process. pdv was the value which was equal to reversible process work. Okay, it was 5. So this value, we come to know that this equation not valid for reversible irreversible process. Now next we are going towards the third equation. TDS. Okay, TDS was, this is a property, right? The property will not change even if I replace it with reversible process, the value will not change. So TDS was equal to dq value was 10 and du value was 5 and pdv value was, previously it was 5. Even if I am changing the process, the values are not changing because these values depends upon the path functions. Okay, so this value equation is valid for both the reversible process as well as irreversible process. Okay, this was generally basic approach which we followed, but now the discussion is not yet ended. Okay, now the discussion continues that, sir, you are telling that w equal to pdv, right? dw equal to pdv. All right, so pdv is the area of the curve which is projected on the volume axis. Okay, now if I change the process, then of course the path is going to change, no? So then pdv value will change, area will change, pdv value will change. Then why you are taking pdv value as same as dw, as same as 5 units? Why you are taking? Okay, so the doubt was real, that I am changing the process. But if you look at the concept of dw was equal to pdv. So if you change pdv was, the area it will change, the work done will change. So why we are taking the same value as reversible process? So the answer for this is that, so generally pdv is not a path function. Okay, pdv is not a path function. pdv is actually a point function. It is a differential. We can integrate it. We can integrate it in the sense it is a continuous function. Okay, continuous function. There are fixed PV values. Okay, it is a continuous function. We can integrate it. Okay, so it means that, suppose for example, the one statement which is most important, it is that between the two endpoints only one process is valid. Between the two endpoints only one process is valid. All right, so between the two endpoints not more than one process is not valid, but we are assuming that processes are reversibles. Okay, between the two endpoints more than one process is valid, we are assuming that, but practically more than two reversible processes are not valid between the two endpoints. Okay, because they will not meet, ऐसा करके सर बोला था. Why they will not meet, I don't know. Okay, so p1 1 to 2. Okay, so if I replace it with next process, then the pdv value is actually not defined for reversible and irreversible process, right? For not defined for irreversible process, but it is defined for reversible process. इसका मतलब क्या है कि if you want to find out the dw value, you will integrate the pdv, or you will project the area on the volume axis. But for the irreversible process you can't project the area on the volume axis. Why? Because the pdv for the irreversible process is not defined for the irreversible process. pdv is only defined for the reversible process. Okay, pdv will not we didn't define for the reversible process, we defined for the reversible process. Okay, you cannot simply project and you cannot find out the area. Okay, we only define for the reversible process. So how to calculate for irreversible process? We can't मतलब कोई नहीं का ये नहीं बोला, बट द कॉन्सेप्ट अंडरस्टैंड करने के लिए इतना समझ लो कि फॉर द irreversible process dw will be less than pdv. Okay, pdv is not going to change for the irreversible process, but dw value now it will be less than the irreversible. So that is the concept of irreversibility. For the reversible work is greater than the irreversible work. Also irreversible work is less than reversible work.
Okay, dw value will decrease. Actually, your doubt was right. Dw value will decrease, but pdv value will not change. PD is not defined for pdv value will not change because pdv is not dependent on the path. dw depends upon the path, and pdv value will be constant for reversible process as well as irreversible process. It only depends upon the 2 points. It is a point function actually, pdv. But if you talk about dw is a path function, okay, you can't say dw of reversible is equal to dw of irreversible, but you can say that pdv for reversible is same as pdv as for irreversible. For irreversible process, dw will be less than dw work done for reversible process. But for the simplicity in analysis, we assume that uh, between two endpoints more than two processes exist, two reversible processes exist, but in practically between two endpoints more than one reversible process is not possible. So therefore, when you look at equation tds equal to du plus pdv, here each and every is path function, point function. So point function does not change between the two endpoints. Okay, so this is valid for reversible process as well as irreversible process. I think this is the thing. Okay.
Okay, I think we discussed till TDS equation. Okay, now next equation was h equal to u plus pv. Okay, so if you differentiate with respect to if you differentiate this equation, dh will be equal to du plus pdv plus udp. Okay, so du plus pdv again gives you dq. So if you replace it with tds, tds will be equal to dh minus udp. Again, this equation is valid for both reversible process as well as irreversible process. Okay. Alright, so this was a case. Now we are going to discuss about the slopes of the various processes. So for isothermal process, slope is 0. Okay, so slope is 0, theta is 0. For isentropic process, theta is infinity, theta is 90, slope is infinite. Okay. Okay, to find the slope of volume, constant volume process, we need to go with the equation dq equal to du plus pdv, right? So pdv will be equal to, and dq can be written as tds, and du can be written as cvdt, right? So from here you come to know that t by cv gives you slope, and t by cp gives you slope of pressure axis. So since cp is greater than cv, then the slope of the volume is greater than slope of pressure. Okay, so this was the concept of slopes of various processes. Now we are going to uh, understand the physical meaning of entropy. Okay, statistical view. So generally, what is entropy? Okay, entropy is a measure of molecular disorderness. Okay, what is disorderness actually? Disorderness is nothing but uncertainty about the position of the molecules at any instant of time. Okay, what is uncertainty? Uncertainty in the sense it is a probability, right? What is probability? Probability is a measure of uncertainty. Okay, in 1977, Boltzmann came and he told the entropy is as a thermodynamic probability, and he gave the equation S equal to K log W. W is the number of microscopic states which are available to identify the particular condition of the system. Okay, uh, so what are the microscopic states? So suppose for example, if you consider a die. Okay, if I consider a die, then consider a 3 die. Okay, uh, consider a particular one die, and if I considered only one state. Okay, only one state, that is, let me take one number on die, right? One. Okay, that is one particular state. Wait. Right, so if I want to get 1 3 times, what is the probability? Probability is only 1. Okay, the probability is 1. Then
change in entropy will be equal to 0, and change in entropy can't be 0 according to third law. Okay, and if you want to achieve entropy is 0, then I must go to absolute 0 Kelvin. Absolute 0 Kelvin, internal energy is 0. Why internal energy is 0? Because internal energy is a function of temperature, right? So that's why internal energy will be 0. So suppose if I take two states, okay, if I want to get 1 2, so how can I arrange 1 2 1 2 1 1 1 1 2? What does this indicate? It indicates that what is the probability of arranging. So probability will be 4, sorry, probability will be 3. I can arrange in 2 1 1 or 1 2 1 or 1 1 2, right? So probability is 3. So generally what does this mean? Okay, if I, suppose for example, if there is a room, I can define the temperature of the room as 25 degrees Celsius. Microscopically I am defining the particular state of the system, but microscopically when I see there are millions of molecules, right? And there will be millions of states. Okay, millions of states. Suppose for example, if entropy is coming as 10, now what is the probability? Probability is that number of microscopic states available to identify the system, okay, increases. The number of microscopic states increases, then uncertainty increases, randomness, disorderedness increases. Okay, disorderedness. So for only 10 there is thousands of lakhs of millions of microscopic states which are needed to be defined. It means uncertainty increase. So similarly entropy, it will be 10 to the power of 23. So you just assume how many microscopic states will be there and how many millions of trillions of molecules are there. How will you define the states? Okay. That is the case. So next we are going to discuss what are the applications of entropy. Okay, so now we are going to discuss the applications of entropy. Okay, we discussed about the physical meaning of the entropy previously, but now we are going to discuss the applications of the entropy. Okay, for the gases, if you talk about the gases, then there will be molecular spaces in the gases, right? Molecules move in the random direction. The molecules are more random in motion, right? So it is difficult to predict the microscopic state of gases. So is more when entropy of the gases is more when compared to solids. Okay, when we talk about the solids, molecules oscillate in the solids. Okay, entropy is not zero in the solid, but molecules try to oscillate, vibrate inside the solid. Okay, so it makes an obvious sense that the randomness will be less when compared to gases. Okay, and that is the concept. Entropy increases, but if we supply the heat to the solids or gases, then entropy will be increased because randomness, molecules will try to collide with each other and they will try to move. Okay, right. So free expansion, what is the case of free expansion? If we talk about the case of free expansion, it is an isolated system, right? It is an isolated system. Suppose if the gas is at high pressure and evacuated chamber, if we take the system is isolated. Okay, dq is 0. Okay, energy is constant. Even though the energy is constant, if we remove the partition, then gases will expand. The gases will expand, the volume is changing, right? If the volume is changing, if the in some less volume, the molecular sphere is there. So entropy was there but less. If you remove the volume, so if the volume is increasing, then actually the entropy value is increasing. Okay, so if you talk about W will be 0 for the free expansion. Okay, so energy is constant. If you apply the first law, ds of irreversibility, dq by dt of irreversible plus delta generation equal to ds. dq by dt of irreversible will be 0. Okay, delta generation will be equal to ds. Okay, delta generation is positive, you know. So entropy increases. Okay, this is the mathematical proof. What is a theoretical proof? That volume is increasing. If the volume is increasing, random is increasing. Like universe is expanding. Okay, here entropy of the universe is increasing.
And the last point is that, suppose for example, entropy gives tells or talks about the quality of the energy. Okay, suppose for example, if the reservoir is 100 at 100 Kelvin, okay, it is rejecting some heat. Okay, so we can utilize that energy to produce the work. Okay, to produce the work, we are converting low grade into the high grade energy, right? So we will get, suppose for example, 100 kilojoule. Okay, entropy will increase. Why the entropy will increase? Entropy will increase, it's fixed and okay. So again, if 500 Kelvin is another reservoir, and if I want to extract to room temperature, then the entropy will increase. So the entropy is increasing, then can I say that the quality of the energy is decreasing? Energy is constant, but quality of the energy is decreasing, right? So that is the thing. Alright, so now entropy changes for the ideal gas. For the temperature and volume, one point you need to know that to derive this equation, you just use the equation TdS equal to du plus PdV. For the temperature and pressure, you use the equation TdS equal to du plus dH minus VdP. Okay, you use those equations. Alright. Okay. Right, so there is some small derivation. Okay, you can derive it. And temperature, pressure, you use the equation dH minus VdP. Okay, for the pressure and volume, just replace R with Cp minus Cv. Okay, Cp minus Cv. From the ideal gas equation, you will get to know that S2 minus S1 equal to Cv. If it comes Cv, first of all Cv, start with Cv. Okay, Cv log P2 by V1 plus Cp log P2 by V1. Okay, this is the concept. For the first equation, Cv log T2 by T1 minus R log V2 by V1 plus R log V2 by V1. Next equation, in pressure and temperature, Cp log T2 by T1 minus R log V2 by V1, P2 by V1. Okay. Look, if there is a temperature and volume, just remember this equation like this: S2 minus S1 equal to, if it is a volume, right? Cv log T2 by T1 first of all, plus in the volume plus R log V2 by V1. In the pressure, we use the equation dH minus VdP, right? So minus will come. Okay, so Cp log T2 by T1 minus R log P2 by P1. Okay, and the next equation of pressure and volume, S2 minus S1 equal to Cp log V2 by V1 plus Cv log P2 by V1. Okay, you can interchange because positive symbol is present. Okay, that is the concept. Next we are going to discuss about the entropy change for the reservoir. Okay, this is one of the important concept which is directly involved in solving the problems. Okay, suppose what is a reservoir? Reservoir is an infinite body which has an infinite heat capacity. Okay, so source what it does, without going any temperature different, it supplies any amount of heat. Okay, sink, it absorbs any amount of heat without undergoing a temperature difference. Without undergoing a temperature difference, it means that temperature is constant, right? So if the temperature is constant, then we can write as ds equal to q by t minus q by t for the source and plus q by t for the sink. Okay, from where this formula came, q by t, ds equal to q by t. So from where it comes means, if you integrate ds equal to dq by t, right? If you integrate, then we will get ds equal to 1 by t, right? 1 by t dq. So q by t. Okay, t is constant, right? It will come out. So this equation we use. But question arises that why we are using ds equal to dq by t reversible. This process is irreversible, right? So if we extract the heat, the process is irreversible, heat rejection. So why you are writing dq, taking dq by t, ds equal to dq by t reversible? Why not dq by t irreversible as delta H generation? As you can notice here that since the temperature is constant, okay, since the temperature is constant, delta H generation is a function of temperature. As you know, delta H generation is a function of temperature. Delta H generation is internal reversibility. It is mainly the function of temperature. If the due to some sudden combustion process will take place, temperature will increase. If temperature will increase due to friction, internal reversibility will increase. Okay, so if the temperature is constant, then can we say that delta H generation will exist? It will not exist. Okay, it will be zero. Then ds equal to dq by t irreversible. Okay, we can't say that process is irreversible, like without by seeing the system we can't decide the process is reversible, right? By seeing the universe we can decide.
Okay, suppose for example, in this case, by seeing the system, if entropy is coming as positive, we cannot say that process is reversible or irreversible. Okay, by seeing the universe, we can say, suppose if the universe is coming as positive, then we can say the process is irreversible. All right, if ds is coming as 0, then the process will be reversible. Okay, that is the case here.